go back. So here briefly, on the left is the unstable basic flow, and on the right is the temporal mean flow, so the average over a period of the DNS flow. And here, to summarize the equations that we use for this frequency prediction by using the mean flow, we have the stationary Navier-Stokes equation satisfied by the basic flow, and we have the linearized Navier-Stokes equation over the stationary solution, which reduces to an eigenvalue problem. And here we have the linearized operator about the basic flow. A different approach is to use the mean flow that we compute from DNS in this linear operator. So we do a linearization about the mean flow, and we have an eigenvalue problem with this eigenvalue where sigma is the growth rate and the imaginary part of the eigenvalue is the frequency. So here we summarize the result of the linearization from this paper of Dwight Buckley, where we have on the left the frequency and on the right the growth rate. The thin line here is the frequency predicted by the linearization about the base flow, and the bold line is the nonlinear frequency. We observe that there is a difference between these two, which is expected because we drop the nonlinear terms. If we look to the frequency predicted about the mean flow shown by the triangles, we observe that they match perfectly the nonlinear frequency. Moreover, we have the growth rate predicted shown by the mean flow is near zero, indicating that the mean flow is marginally stable. So this property of the mean flow has been named ERZIF, meaning that the real part of the eigenvalue is near zero, and the imaginary part of the eigenvalue is near the exact nonlinear frequency. So let's give an explanation why it works if you consider an evolution equation and we apply Fourier decomposition. And we look to the first component is the equation governed by the mean flow. The term here is the Reynolds stress term. And the component one that governs the first Fourier mode is shown here. If we suppose that the first mode or the first Fourier mode dominates all the others, so we can neglect the higher interactions, and only this equation remains. And if we look closely to this equation, this is the linearization about the mean flow. So this means that if we have a case where we have monochromatic signal, or in flow where the fundamental harmonic dominates all the other, then ERZIF should be exactly satisfied. So the question is, does this property is universal? And the answer is no, as it has been shown in the two-dimensional thermosolutal convection problem, where we impose a thermal and oscillator gradient of opposite sign, where there is a Hall bifurcation at this threshold, at this Rayleigh number threshold. And when we have Hall bifurcation in this kind of problem where there is an autosymmetry, we have two solutions, a traveling and standing waves, one of which is stable. So here the standing waves are unstable and traveling waves are stable. Just to recall, in this problem, the basic state is the conductive state and the standing waves here. So we apply the same analysis that I showed before, the linear stability, over the mean of the traveling waves and the mean of the standing waves. Here, the blue dashed curves show the linearization about the conductive state, and the red dashed curves show the linearization about the mean states, and the bold curve show the exact nonlinear frequency. If we look to the traveling waves, we observe that the frequency about the mean and the frequency and the nonlinear exit frequency matches, and also the growth rate is near the marginal stability. In contrary, for the standing waves, we observe that the mean in red dashed curve doesn't match the nonlinear frequency, and the growth rate is far from zero. This indicates that for the traveling waves, this ERZIF property is valid, and for the standing waves, it is not. So this property we have also shown that it works in the shear-driven cavity flow and in counter-rotating Taylor-Quad flow, where there is also Hall bifurcations. But so far we have only the standing waves as a counterexample. But earlier, François Galère said that there are many, so maybe we will ask for some details about that. So But here we have to emphasize that the ERSIF property is not predictive, because we need to do a DNS to compute the mean flow. But it is an interesting property for theoretical point of views, as it has been done in the self-consistent model that it has been shown by Francois earlier. So let's give an explanation of the self-consistent model. We go from the equation that I showed earlier, and we focus on these two equations. Here, if we suppose, as we said, that only the first Fourier mode is contributing to the distortion of the mean flow, therefore we can make a further approximation on the Reynolds stress. Here we suppose only the leading mode contribute to the distortion of the mean flow. Therefore, the self-consistent model is built from the mean flow equation by considering only the leading eigenmode and the linearization about the actual mean flow. And this system is solved iteratively until it reaches the condition of sigma equal to 0 by the external load of the amplitude of the mode, and it yields an almost exact mean flow and mode and the frequency. So here are the results that they found. The first figure shows the mean X component. The upper, and this is the Reynolds stress divergence. The upper sides of this figure show the DNS, and the lower side show the self-consistent prediction. And we cannot see any difference with naked eyes between these two figures. So, and the frequencies predicted by the self-consistent model here are shown in purple squares, and we see for the cylinder case, we see that they match perfectly the nonlinear frequencies shown in dashed curve. So here we will try to apply the SCM to the thermosolutal convection, of course, on the case of traveling waves, because we have the ERSIF property that is satisfied. So as before, we only consider the first mode in the distortion of the mean flow and the linear equation, but in this case, we solve the problem with the Full-Newton method to avoid those problems of convergence. Here are the results. On the right is the frequency of the Rayleigh number, and the red circles show the nonlinear frequency, and the black dots are the mean flow predicted from the linearization about the mean flow, and the diamonds are the prediction from the SCM. And as we observe, the SCM does not predict very well the frequency, at least for high range, only close to the threshold. On the left is the amplitude of the first mode. The red one is the amplitude of the first Fourier mode, and the diamond are the amplitude of the first mode predicted by SCM, and we observe also that it does not predict very well the amplitude. What we did is we went further and considered the second Fourier mode in the equations, and therefore we add these two terms here, these two contributions here, and the second equation, and we solve this again with as a coupled system by a Newton method. And here are the results. This is with the SCM at first order, and if we look to the second order, we see a little bit better improvement. To the third order also, but it doesn't cover all the range of Rayleigh number. And if we go to the fifth order, we observe that we get a very good prediction. But to have an exact match or perfect match, we need to consider higher orders. And also, as you have seen in the amplitude, the improvement. So to summarize this presentation, for the cylinder wake, the ERSIF property is valid, and also the SCM. For the thermosolutal convection and for the traveling waves solution, we have ERSIF is satisfied, but not the SCM. And for the standing waves, as I said, is a counterexample to ERSIF, as I said before. So the perspective here, we still have to work to understand in details when this property works, and also when the self-consistent model can predict the nonlinear frequencies, and also are there other counterexamples for RZIF and SCM. So thank you very much for your attention.